I need to remind you about inverses. Remember, if I've got two functions, f of x and f to the negative 1 of x, that means one undoes the other. That means that f of f to the negative 1 of x ends up getting your x back. That is, the inverse function of x does something to x, like squares it or does something crazy to it. Then you take that answer and stick it into f of x, and it undoes whatever this guy did, and you get your x back. One thing I want to remind you is whatever the domain is of f of x, that becomes the range of the inverse of f of x. And whatever the range is of f of x, that becomes the domain of the inverse of f of x. The reason for that is because if I've got some point, let's say a comma f of a, that's on f of x, then its cousin, a point that's going to be on f to the negative 1 of x, will have the x and y switched. That is f to the negative 1, f to the negative 1 of x, let's say, is going to have the point f of a, comma a. And that's going to be true for all of the points. They're going to be switched. The x's and y's get switched. If f of x has a bunch of points, then f to the negative 1 of x is going to have the same points, only with the x and the y switched. And then, of course, if you graph one of these guys, it's going to be the same as that graph, except symmetric about the line y equal x. Let me show you. I'm going to start with sine of x and inverse sine of x. I wonder if I should, did we lose our basketball? Thank you. Maybe I'm going to not do it on this. Maybe I'll just do it on the whiteboard. So it doesn't block the camera. Okay. All right. So here's what I've got. I've got parametric equations, and this parametric equation is x equals t, y equals sine of t, which, since x is equal to t, the first parametric equation is y equals the sine of x. The second parametric equation says y is t and x is equal to the sine of t, so the next one is x equals the sine of y. Do you see that they're inverses of each other because I switched the x and the y? Now, what we ordinarily do is we don't just keep this x in terms of y, we take the inverse sine of both sides of this equation. So now I end up with the inverse sine of x on the left and just y on the right. So really, what I'm graphing is y equals the sine of x and y equals the inverse sine of x. That's the two functions I'm going to graph. Let me see what my window happens to be. Okay, my t is going from negative 2 pi to positive 2 pi. My step is pi over 20. And my x min and x max is negative 2 pi to positive 2 pi. And my y min and y max is positive 2 pi to positive 2 pi. And I get this graph. Here, maybe I'll make it so that you can. Okay, here we go, just a second. Oops. Oops. Alrighty. Here's the graph. Here's the graph of y equals the sine of x, your classic sine, and then here's the graph of its inverse, the inverse sine of x. Now, one thing we don't like about the graph of y equals the inverse sine of x is that it's not a function, right? That is, for a particular x, I have an infinity of y's. For example, if someone asked me what's the inverse sine of 0, that is, they're asking me the sine of what angle is going to get me 0, the answer is there's an infinite number of answers. The sine of what angle gets me 0? Well, the sine of 0 gets me 0. The sine of pi gets me 0. The sine of negative pi gets me 0. The sine of negative 2 pi gets me 0. The sine of pi gets me 0. The sine of 2 pi gets me 0. And we don't like that. We don't want our function to be, or our inverse to be a non-function. So what we have to do is restrict the domain and range of y equals the sine of x so that our inverse guy becomes a function. We want this guy here to be a function. And the only way this guy here, which is y equals the inverse sine of x, the only way that that guy gets to be a function is if y equals the sine of x, and I'll do that in green, is if y equals the sine of x has its domain restricted, alrighty? So, because this is -1 to +1 for the inverse sine of x, and this is pi over 2 to -pi/2 for the inverse sine of x, I'm going to have to, and maybe I should do that in blue instead of green. Oh, well, too late. But so for that reason, I'm going to have to restrict my sine, which I am doing in green. Here's my sine curve. I'm going to have to make sure my sine curve is 1 to 1, so that the inverse of this green sine curve, which is the blue inverse sine curve, is a function. And so looking at the sine of x, I have to designate my domain of y equals the sine of x to be -pi/2 to pi/2. And my range is going to be from -1 to 1. And because I've designated that as the domain and the range of my sine, so that my sine can be 1 to 1, that means that the domain and range of my inverse sine are reversed. The domain of the inverse sine is going to be from -1, from -1 to 1, and the range is going to be from -pi/2 to pi/2. And the same sort of thing happens for cosine and tangent, but I'm just going to do sine for now. Why do I care about this? Well, I'll tell you, because you need to know this in order to understand how we get the derivative of the inverse trig functions. And that's what I'm going to show you right now. Okay, I'm going to make this go away. Whoops. What am I doing? This is not something you have to memorize per se. It's just something I want you to look at and learn from. Here we go. I want to get the derivative of the inverse sine of x. Well, I know what the domain and range of the inverse sine of x are. I found them just now with that discussion of the green versus the blue graph. And so let's go for it. Sine of y equals x. Do you see how this can become that? All I did was take the sine of both sides of that formula, and I get sine of y equals x. And now I take the derivative of both sides, but it's an implicit derivative. So the derivative of the sine of y is cosine y times the derivative of y with respect to x. The derivative of x equals 1. So the derivative of y with respect to x is 1 over the cosine y. Yay, so far so good. The problem is I want my derivative to be in terms of x, not y. So I go cosine squared plus y, sine squared equals 1. And so cosine of y equals plus or minus radical 1 minus sine squared y. But here's where my discussion about domain and range comes in. Y only lies between -pi/2 and pi/2. And since y lies between -pi/2 and pi/2, those are values in the first and fourth quadrant. Those are values for which the cosine of y is always positive. So I don't need to have the plus or minus there. I don't need a plus or minus in my answer here, because cosine y will never be negative. because y ranges from negative pi over 2 to pi over 2, and cosine's always positive on those values. So I get to just put positive. And then finally, since sine of y equals x, I get to be 1 over radical 1 minus x squared. And there it is. That's the derivative of the inverse sine of x. So generally, and you may want to write this down, generally, the derivative of the inverse sine of u, where u is some function of x, is 1 over radical 1 minus u squared. Except then you have to multiply by the derivative of u with respect to x, because of the implicit differentiation. You guys okay with that? No? So
Yes.
that's, well, go ahead.
I just said yes.
Good enough. So that's it. So the only thing you're going to have to memorize is this, that the derivative of the inverse sine of u is equal to that. But I just want you to know that it's not magic, it actually came from somewhere. All right, well, let's get the derivative of the inverse tangent. Here we go. Derivative of the inverse tangent of x. I got y equals the inverse tangent of x, which means tangent y equals x. When I take the derivative of both sides of the equation, I get secant squared y times y prime equals 1. I have to sprout that y prime because that's an implicit derivative. Then I solve for y prime, I get 1 over secant squared. Then I do my I tan in a second thing, which I can never remember. So I end up just starting with cosine squared plus sine squared plus 1 and dividing each and every term by cosine squared. And then I get my I tan in a second thing, which I can never remember. And so I substitute 1 plus tangent squared y in. Now tangent squared is what?
Mr. Shannon's eye, please.
What do software update? Apple.
Updated.
Apple is, I don't update anything. And, tangent squared is always positive, so there's no ambiguity there. And tangent of y equals x, and so I get a 1 plus x squared there. And so generally, the derivative of the inverse tangent of u is equal to 1 plus u squared times du dx. Well, that's looking like a y there, but it should be a u. My u has too long of a little tail. So that's the thing you're going to have to memorize, is the derivative of the inverse tangent of u is equal to that. Boy, that thing really vibrates, doesn't it? Yeah, my goodness. Okay, and then similarly, and I'm not going to go through the awful details, we get an expression for the derivative of the inverse secant, which is 1 over the absolute value of u times radical u squared minus 1. And the reason why that u's absolute value is very interesting, it has to do again with domains and ranges, but I'm not going to go through it because it is fine, it doesn't matter. Just you'll have to memorize that as well. So that's the backwards of sine. Sine is 1 minus u squared, secant is u squared minus 1, except you have to have that absolute value of u out there. I just found the derivatives of the inverse sine, secant, and tangent. What about the cofunctions? Well, there's a relationship between a functional value and its cofunctional value, and that relationship is given by this. For example, inverse cosine of x is equal to pi over 2 minus inverse sine of x. Another way of saying that is, let's say it's a half. Are you guys okay with that? The inverse cosine of a half is equal to pi over 2 minus the inverse sine of a half. That is the inverse cosine of a half. The cosine of what angle gets me a half, and that's going to be pi over 3. The inverse sine of a half, the sine of what angle gets me a half, well, that's pi over 6. And you get your relationship. Essentially, that's just saying that the sine of an angle and a cosine of an angle are always complements of each other. That's all this is saying. Well, that sort of thing happens with secant and tangent, or rather, secant and cosecant, tangent and cotangent. And so you end up, if you take the derivative of both sides of an equation, do you see that the derivative of one guy is going to be the negative of the derivative of the other guy? Because they have that relationship here, that negative there. So it turns out the derivative of the cofunctions are all negatives of the derivative of the functions. So now I'm going to summarize this on the board, and then I'll be done, because the rest is for you just to, not today, but tomorrow night, to just, you know, mindlessly plug into these formulas. So what you learned is the derivative of the inverse sine of u is equal to 1 over the square root of 1 minus u squared times du dx. And so the derivative with respect to x of the inverse cosine of u is just the negative of that. Sorry. And so on down the line. You know, your tangent, whatever your tangent is, your cotangent is the negative of that, and your cosecant is the negative of that. And that's it. There's nothing more for me to teach about this. So good luck doing problems.